And then I'd like to know if you can see the shared screen so we can go on. So if you can see the shared screen, maybe just a thumbs up would be okay. Then we are good. All right. Okay. Thank you. All right. So for our session today, we'll be dealing with these. We'll be addressing these objectives. We hope at the end of the session that, all participants will be able to simply do these things. That's one, be able to import and utilize Python packages. Also, we'll be delving more into Numpy, and so we'll want to be able to generate um, an array and then also make use of some of its attributes and possibly save it to a file. That's a text file, a CSV file format, and then also be able to read the data sets from the file using the Numpy or the NumPy, depending on how you would pronounce it. And then we would also want to be able to subset the data using the same NumPy. And we would like to, at the end, also perform some basic arithmetics in NumPy. And then we would also try to plot some of the um, ASCII data that are data sets. We'll try to visualize some of them using Matplotlib. And then we'll also try to read, like I said, read data from CSV, but this time we are going to generate them or produce them on a spatial plot using Cartopy. So I don't know if probably we all installed Cartopy, but I believe we did that on the Sunday. So if not, you just use conda to install. So conda install Cartopy or conda install dash force Cartopy to force it to really install in the same environment you are in. Or you can also use pip. So pip install Cartopy would work. And we'll also try to load shapefiles into Cartopy maps and then use the default Cartopy shapefiles. And we would also look at, the basic Cartopy map layout and how we can sort of improve on that using our own shapefiles. So like I was saying, if you haven't installed it yet, you can just, you know, preceding with the exclamation sign in here, you just type pip install and then your Cartopy. Okay, sorry. Pip install Cartopy and then you are good to go. All right. Or conda install Cartopy and then that would install it directly from there. Um, I intentionally showed this here because most of the packages we'll be using in Python, you can actually find them here. So whatever package you need for whatever you want to do, maybe you want to do translation, you want to do maybe audio to PDF translation, and you need an application that will do that, you can just type it on pypy.org. That's PYPI, okay, .org, and you have a whole lot of packages. You can just click on it, see what the documentation is, and then use it as suitable or for what purpose you'd want to use it for. And also, pip actually is a wider community, so it allows for people to also build or to add on to people's build. So if you are quite versed in the Python programming language, you can also make some contributions onto some of the packages and also probably even build your own package. And that would also come in handy for the community. All right. So that's just by way of introduction. We'll get started and we'll start off with some basic understanding. So the Python programming language has lots of libraries or what we call packages. It has lots of packages for almost every activity you want to do. And then definitely as we are making advancements in science and research and also in um, general activity, we also want to be sure that we have the computational capacity to support, right? And so the packages come in handy for this task. Um, Just a quick one, please. Douglas, please just a quick one. If you can hear me, is it possible just to meet you in front of the class? Just a quick one.
I can hear you.
Okay, so I'm wondering if those on the YouTube page are also getting the audio.
Yes, the audio is working now.
Okay, then that's good. That's good. All right. Okay, so like I was saying,
Yes.
so like I was saying, the Python packages are suitable for, the growing advancements in technology and then the various activities you are doing. And so, rather than going to run the whole procedure or the whole process from scratch, the packages come in very handy for this purpose. So we have some of them being Numpy, SciPy, Matplotlib, Pandas, SymPy, Seaborn, and we'll try as much as possible to look at all these packages I've listed here in this training, either today, tomorrow, or the very final day. Okay, and they have very huge functionalities. So we start off with how to import or load the package. So we have different approaches. One, you can just import the package. Say we are importing NumPy, you can just type in import NumPy, and then it would import the package. Now the one thing you would need to note is that when you import a package, it comes with all the sub packages under it. So you have like a big parent package, and then there are sub packages for addressing certain specifics. So if I just import the package, it would come with all the sub packages under it. Now, the second option is I can import the package as a very short name. So what I'm doing here is that think of it as, humans having sort of nicknames. All right. So you probably have a very long name and your friends decide, okay, maybe that's too long to call you by. So they would maybe abbreviate your name and then use just maybe a nickname, something just to refer to you. Once they mention that name, you know they are calling you. You get it. So once you are called, you come with everything that is within you. You come with all the packages that are within you. So it's the same thing here. Once I'm importing a package as a certain name, it means whenever I call that name, the name substitutes the package and it comes with all the packages, um, sub packages. All right. And we can also be specific and indicate that from this package, import the sub package item. So I'm trying to say that, okay, go into the package we are dealing with and then import a specific sub package. Right? And same way we can import just that specific sub package. And if the specific sub package probably has a longer name, we decide to also give it, you know, an abbreviated name. Right? So that's these are some of the ways you can import um, packages and make use of them. So let's start off with the NumPy. So NumPy, as the name implies, is just num for numeric and then pi for Python. So anything numeric, you can do that with NumPy. Anything that has to do with, the numerics, dealing with numbers, dealing with arithmetic, dealing with equations, operations, you would be able to use the NumPy for that. And there's a link for some documentation. All right, so if you have the notebooks, it will be quite easy to work with. If not, we can also try to recreate from scratch. Maybe open your Jupyter notebook and then work along with us. So we said the first option is just import NumPy. Now, if I import this, it means for me to make mention of the package, I would always have to call NumPy. So let's say I have a list, say a list containing 1, 2, 3, 4, and then I want to find the sum of the items in the list. Okay, I want to find the total of the items in the list. That's when I add them up, what I would get. Now, because I've imported NumPy, I would need to call NumPy in the full form. So NumPy here. I'll need to call NumPy or NumPy in the full form and then call the sub package. Let's say sum. Now, what this is the parent dot the child. Okay, so the package dot the sub package. So imagine your name is OneQuantum Ghana, right? And then say OneQuantum is the child of Ghana. So all we would do is that we call the parent, which is Ghana, dot their child, which is OneQuantum, all right? And if there's another sub package, let's say another child of OneQuantum, so in this case the grandchild of Ghana, then we can also go down to dot the next child, all right? So that's how you make use of your packages after importing. Always a parent dot the child, parent dot child dot child dot child, in that order. So we want to make use of, say, numpy dot sum. Want to make use of the summation. So numpy dot sum, and then we pass this on our list A. Okay, this will just give us the sum of the list, and that's one way of making use of the package. Now the second option is, we said we can just import the sum from the numpy. Now you notice that since we imported numpy from here, we can make use of the other sub packages of numpy. Say numpy dot mean, and we are finding the average of the A. It's possible to run this and we just get the value, right? Now the other option is, we are importing just the sum from numpy. We are saying that go into numpy, don't bring any other thing, bring only the sum. Okay, so I call this, now it means this is slightly different. If I restart it, it means our numpy would be deactivated. So let me try restarting so that we don't get access to numpy again, and then that would explain clearly what we are doing. So if I type numpy here, there's nothing called numpy because it's assuming that we've not loaded it because we've restarted. You notice the input number here is 1. That means this is the first time I'm running the cell. So numpy hasn't been called in this restarted mode. So now if I import sum from numpy, then it means I can only make use of the sum because that's the only item I imported from numpy. So let's say I have my A to be 1, 2, 3, 4, the same, and then I find the sum of A. Bear in mind, here I've imported the sum from numpy, so I don't need to call numpy.sum because it knows that I called sum out of the package. So if I run this, this would work because I've imported the sum. Now, if I decide to find the mean, and I just type in mean of A, this will produce an error because we didn't import the mean from numpy. We only imported the sum. All right, and so these are things you would need to watch out for. Also, the other option is we can just import, the two of them directly from numpy. Say, okay, from numpy import sum, comma, mean, comma, multiple sub packages, and it works. And we can also say from numpy import sum as s. Now in this case, it means if I want to make use of the sum, I can just call s because I've given it the representation of the letter s. So if I type if I just type s on our A, which is the list, it would give us the sum of the A, right? And that's how to also make use of the import in that case. Now the good part of this is that if your package name is very long and you use a very short abbreviation, you easily call it. That's the key benefit, and it's very easy to identify it too. And for this particular notebook and this session, will be importing numpy as np, which is that's more like the de facto standard mode. Almost every Python programmer understands what np is. Everybody understands what imports numpy as np is, and so it's easy to work with this. So we import numpy as np for this work, and then now if we want to call the sub package, it means we would make use of np dot the sub package. All right, so in this case, say we are finding the mean of this A, and so np dot mean of A. If I want to find the standard deviation, np dot std. All right, standard deviation of A. And bear in mind, this is a method. This is like a function, so it comes with the open and close brackets. I said there are some exceptions to functions that have parentheses, but these ones are standard functions from numpy, which will definitely come with the open and close parentheses. All right. And yes, also one thing to note is that if you are not so sure of all the packages in Jupyter Notebook, I believe it's even the same in Spider and then some other IDEs. So if I've imported numpy as np and I type in just np dot and I hit my tab, I expect it to list the sub packages under them. Okay, so we have apps for absolute, you have add docstring, a whole lot of things that NumPy can do, right? And the same way, if I select one of these which has a sub package and I hit the dot and tab, it would give me the list of also the sub packages of that particular sub package itself. Okay, so that's pretty much how it works. And also, if I want to see how this is used, when I have my np.std and open my parenthesis and close it, in between it, I can hit my shift and tab, and then it will give me a help on how it's used. So it means there's the way to use the np.std. You need your data, which is in this case termed as A, and then these ones are optional. You can specify the axis. So if I have data of multiple dimension, I can find the standard deviation across a particular dimension alone. And then I can also specify the D type. For instance, I have data of different formats. I can specify, okay, the data sets are all to be treated as floats, they're all to be treated as strings, treated as, default data types. That means I'll pass in none. And then maybe the out, and then the degree of, your, these are more statistic terms. So if you're finding your standard deviation, you know the degree of freedom and all that. And a lot more of other sub information you can get from there. So you can always use the shift tab within the parentheses to know what the function is, what it does, and then some examples of how to use it. Okay, so that's it. And then also, if you are not conversant with this, what you can do is to precede it with a question mark. And sorry. So I precede the np.std with a question mark, and then I have the help. So in this case, I don't open and close the parentheses. I just precede it with a question mark. That will produce the help. Okay. Or alternatively, you can just type in here help and then pass this into the help function, and it gives you some extra detail on the documentation. Right. So we're going to try our hands on some basic arithmetic. So like we said, we can find the maximum of the values you're having. Say this is a list of integers. We find the maximum value in here and tells us the maximum is 8. All right. We can equally find the absolute, the maximum absolute value. So let's say np.max into bracket np.absolute. We open, and so we have to close the parenthesis here too. And in this case, we expect the maximum value to be 20 because it finds the absolute, then gives us the maximum. Right. Now, if I also want to find the position, not the maximum value, but then the position of the maximum value, then I'll need to have the argmax. Okay, that's like telling us the position of the maximum value. Means it finds the maximum value, tells us where it's located. So this gives us index of 4. Bear in mind, this is Python indexing starts from 0. So 3 is at index 0, 1 index 1, 6 index 2, negative 20 index 3, and then 8 index 4. And remember, the maximum value was 8. So the position of 8 is at index 4. You can also sort your data, your data set. You can sort it, and you would have it in the increasing order. You can also do this in the reverse. In the np.sort, when we tab, we can see some detail on it, and then it tells us the approach in which we want to sort the data, the order we would want to sort the data, and a lot more, some examples beneath which you can try your hands on. Okay, we can also find the minimum value, and then we saw yesterday creating a range of values, and then we then had to loop through, and I indicated from there that if I type in, say, range of, say, 152, is going to create a range of items. Even though this produces range 152, it means it's having the element 1, then plus 2, which is 3, and then it ends before 5 because our step here is 2. Okay, but then we can also use the np to generate the same range. So let me make this start from 0 to 5 in steps of 1. That means it's from 0 to 4. Now we can also produce the same thing using the np.arange. Okay, so there are a whole lot of range methods. np.array would create the array. We can also use np.arrange to create a list of items of this magnitude. We can also pass in here the starting point. So I can have the starting point, the end point, and then also the step. And this will produce something like the first one that we had. Okay, so if I do not specify them, then it means it's going to use the default start point, default, the stated or default endpoint, and then a default step of 1. So we can use the np.arange to create a range of items. And then we've already seen the absolute. We can also use the round function to get to round our values off. So let's say I have here np.round, and I tell it to round the value 2.356 to 1 decimal place. It gives me the rounded form, and that's it. And we also have some trig functions, so we can find the sign, and I'll explain something in a bit, okay, which has to do with the sign. Okay, there's more. You need to be a bit. You need to understand how it works in order to use it. Else, you might. Let's say we have this. Let me even explain it from here. So we all know sine 90. All right, sine 90 is 1. So if I find here sine np.sine of say the value, I believe you can still hear me. Right. So please, if you can hear me, just show a thumbs up so I know I'm still clear. Hello. If you can hear me, kindly show a thumbs up so I know I'm still clear. Okay. All right. Thank you. All right. So like I was explaining, the np dot sine of 90, we expect that to produce 1, and that's because it's treating the 90, and they are already taken in their degree forms, but then we need to first change them into their radian formats in order to get the exact value. So first I need to convert this 90 from degree to radian. So I have here np dot deg to rad, which is the degree to radian conversion. So it changes the 90 degrees into, sort of pi radians format, and then finds the sine of it. And that's when this works, right? And it's the same for, the cosine. So using this, you need to be a bit, you need to know what you are doing, and yeah, you need to know what you are doing and then be able to tweak it, right? Sorry, why am I getting this? All right, don't worry, I'll come back to this because I think there's another example down there. I'll use that to explain it clearly. All right, so that's cool, no problem. Okay, so we can also, like I said, we can round this value up and say maybe I have a multi-dimensional list. Now in this case, this list of the first dimension containing 1, 2, 3, the next dimension containing 4, 5, 6. So we can find the shape of the A. I expect this to produce an error, I believe. Yeah. So if I want to find the shape of the A, I can make use of the np.shape to find the shape of the A. That's because the list hasn't got an attribute of shape. So I make use of my np.shape of A, and I get that. So it tells me the shape of the A is a 2 by 3. Same way I can transpose the data, okay, from the way in which it was into a transposed format. Now bear in mind, we can also make use of the .t approach, okay, but this wouldn't work for a list. It works for an array. So if I try this for a list, I expect attribute error because the list hasn't got np.transpose instead. Okay, and we can also use this to convert a list to an array. So let's say in this case we created our A, and our A is a list. So by checking the type of A, we notice it's a list. I can just make use of np.asArray to change whatever format it is in into an array. So if I now check the type of my new variable A1, it tells me there's an array. Okay, and we can equally, try the transpose of the array. But then you notice that with the array, it's just simple to even do just the array dot t, and that transposes, unlike the list. Okay, and we can also make use of the np.transpose method to transpose our data. There are some extra things we can try our hands on: the shape, the size, the dimension, and then also you probably would, let's say in the case of you are testing a certain function, or you are testing a code or a model or something on certain values, and you want to create random values. You can make use of the np, and under that there's a sub package called random, and under the sub package there are other sub packages. One of them is random, so I can just use np.random dot the random and then generate 20 random numbers. And once we do this, we can see a range of numbers. We can also make use of the dot rand, which will still produce also 20 random numbers. Okay, and we can make use of the rand n, which would include negative and positive numbers. So if I want to test my script or whatever code I'm having, or whatever model I'm testing over negative and positive numbers, then I make use of the rand n, and that generates positive and negative numbers as well. And we can use this approach to produce, random integers alone. All right, we are creating integers. In this case, you notice the first one we had decimal points or floating point data types. Now we would want to just have integers alone, so we can make use of the rand int, and then we indicate the least value, and then the highest value, and then the size. So we want values between -1 and 2, but bear in mind 2 is not inclusive, so the highest point is exclusive. So we are starting from -1 to the integer closest to 2, which is 1. I want to generate 30 samples of that. Okay, so this creates 30 samples of negative. Let's say if I have -5 all the way to 6, so I want the values to range between -5 and 5. So I can just use this to generate random numbers within that range. And these are some of the beautiful aspects of using NP or NumPy. We'll still come back to a lot more, but let's just switch to SciPy in a bit. I don't know if there's a question on what we've done so far on the NumPy. I could address them before we move on so that we are at par. If there's any question, I'll take them right now. If not, we can move on. All right, so I assume we are okay since there's no question. But then if you still have a question, you can type it in the chat, or you can type it if you're on a social media page, you can type it in the comment button, and I'm sure Dorcas will be able to identify and then read it out to us. Or you can also step to the front of the class where the podium is and ask your question. The same way, just as we did for the NumPy, we can also import SciPy, and in this case, as a standard, import SciPy as SP. And bear in mind, SciPy is just scientific Python. So everything that NumPy does, SciPy also does same. I stress that SciPy can go to, all right? And there are also some things that NumPy gets to do. So they are basically almost the same. So let's say finding the sum, I can also try sp.sum of a, and that gives me the sum of the list. I can also round these values, all right, using the round underscore in SciPy to 2 decimal places, and then that would round a range of items. Bear in mind, whenever you see the underscore, it means you are not just doing that for one value, you are doing that for like a list. So in this case, because our A is a list, we can't make use of just round, but rather the round underscore. And these are some special sub packages. It's not for all packages though. So we can do same for the integers. If I want to do integer conversions, I can make use of int underscore, and that should also work. And then I just brought in just so we know if I'm making use of my code and I'm getting all these warnings telling me that some of the things will be obsolete soon, right? And some warnings, not necessarily errors. These are not errors. They are only prompting you to make use of the filter warnings sub package under the warnings main package. And then there are various ways you can treat the warnings. Either you want to ignore them so that they don't show at all, or so if I should run this, it means I don't want the errors, the warnings to show. So go back and if I go back and rerun this one, I don't expect the warnings to show. Okay, I didn't import SciPy. So we import and then we run this. This time the errors, or the warnings, not the errors. The warnings do not show because I've ignored them. All right. Okay. And then we can also do a lot more. So virtually same and some extras. And then we also have what we call the Matplotlib. All right. Now this has some plotting functionality similar to MATLAB. So if you've used MATLAB for a while, you know, I mean, some of the syntaxes we'll be using are quite similar. They are not so different. All right. And there's a plotting library. It contains a whole lot of sub packages. This is useful for, I mean, creating multiple dimensional plots, one dimensional plots, I mean, changing the colors, I mean, the color maps, the skills, I mean, the figure interface, anything that has to do with plots, you can make use of Matplotlib. Now, these are not the only, there's not the only plotting library, there are other ones, but most of the other ones make Matplotlib, they actually built on the Matplotlib. So even in pandas, you see a plotting package that is built on Matplotlib. We also have the ggplots. We have, I mean, a lot more various plots. Seaborn is one of them, but most all these ones are built on Matplotlib as their base, all right, before they have the enhancements. So there's some extra information to help you on what to do. So if I'm just importing Matplotlib, I can just import it as say MPO, right, and I'm good. Now I can also make use of a specific package under Matplotlib, which is in this case PyPlot. So we can use PyPlot, we can use PyLab, and that's also has a vast array of plotting functionalities. And so we'll be using this one, and we can import this as say from Matplotlib import PyPlot as PLT. Okay, so it means we are importing PyPlot from the Matplotlib, and we are calling it PLT. And the same with this same function can be written as just import matplotlib.pyplot. That means go into the matplotlib parent, import just the pyplot subpackage, and then abbreviate it as PLT. Okay. So if we run this, it means we have PLT and we can make use of that. So let's say we create a random list of numbers, okay, for the variable a, which we've seen this from the NP subpackage. So we create the random list of items, about 400 values, and then we want to plot them. So there's a plotting function under the PLT, which is a matplotlib pyplot, which we've called as PLT. So I'm going to make use of the sub package plot, which is a plotting function. So I also would call PLT dot the function, which is a plot, and then I indicate what I want to plot in there. So PLT dot plot of A should generate a plot of random numbers. Okay, and like what we're having. And once I have a plot, I can, all the things that come with a plot, like setting the Y label, the X label, the legend, and the rest, you can do same. So let's say I want to set a title for this plot. You can just call plt.title and then pass in your title as a string. Say my first plot. Okay, and then we run that, and then the title just shows. And bear in mind, you can change the font size of the title. You can change some attributes of the title. So in here, we can also pass here just font size and give a value, say font size of say 24, and then it changes to suit. All right. Okay. So you can do a whole lot of stuff in here. We can also set the Y label. So we can also have PLT, which is the main package. The matplotlib.pyplot we imported as PLT, and then under it we set our Y label, and we give the Y a label of say random numbers, and then we would notice that it has a label of random numbers. Also, we can change the font size for this one, and we can do same just as we did for Y label. We can do same for X label. So we can have PLT dot X label, and let me call this maybe index. So because that's based on the position. So whenever you plot just a particular variable alone, and they are not two separate variables, it's going to plot that variable against its index or its position. So that's exactly what we have here. So we label this as our index, and we can also change the font size and all that. Now let's say I want to pass in here a legend, so that if I have let's say I have A and then B, so B is also another 400 random numbers. So I can plot A, and I want to plot them on the same panel, so I don't need to create any subfigure. We'll be looking at subplots soon. So I just call plt.plot, and then I plot my B also on the same thing. Now if I do this, it just will shade them by default, but then I don't know which one is A, which one is B. So if I want to make use of the legend, what I'll need to do first is to identify the plots. Okay, so I need to first assign labels to the plot. So I need to pass here a label, which is a string, and in here I'm passing the label to be A, and then I do same for the B. All right. Now, when I give them labels, I have not necessarily given a legend, so nothing would show. There's no legend yet. But then if I want the legend to show, then it means that's where now I would have to make use of the plt.legend. All right. And in the legend, there are a whole lot of things we can set: the location, the handles, a whole lot of things, the marker size, and a whole lot more. Okay. Now, so if I just call this, by default, it would be looking for the labels that we had within the plot. If I don't pass anything in there, it will look for the labels and then position the legend in the space it finds convenient. So if I do this, it just located this point in the bottom and then brought the labels as A and B. So now we can clearly tell that, okay, the blue line is the A, the sort of orange line is the B. Okay. And if I want to be specific, I can then give a location. Say loc equals to, then I would specify maybe upper right, okay, as a string. Then it goes to the upper right. Yeah, I want it to be on the upper left, wherever I want it to be, I can specify. Bear in mind, we can also use numbers because these have numbers. If I use 0, 0 should be the best location. So I expect 0 to take me back to wherever there's convenient space. So it went up here because based on the new, bear in mind, it's not the same plot you are producing all the time because we have our random numbers generated in the same cell. So anytime we run this, the numbers get randomized again. They are changed. So based on the new set of random numbers we had, it identified the right top to be the optimum position to place the legend. All right. So if I want to be specific on maybe a different location, then I can pass in a different value, which shows, so 1 is actually upper right, and then if I pass in the value 2, I think that will give us the location that's upper left, and then 3 is the lower left, and so on and so forth. Now if you want to know exactly where to place them in the plt.legend, you can just hit your shift and tab, and then you have this popping up in your Jupyter notebook. When I hit the plus symbol and then I go through, there's a whole documentation on it. All right. So as I'm going through, you would see the lock is the label, and when you go through, there's a table somewhere that tells you the location and then the code. So if I use any of these numbers, it has an implication. It knows where to go exactly. So from 0 to 10, right? That's pretty much it. So the basic plot, this is what we need to understand, but we'll go into some details of it. So we've clearly seen here how to produce a visualization of our data, how to label it up and then give some extra information. Now let's say also I want to change the range. I want to increase my y limits. Okay, from here it starts from 0 to 1, and then there are some outer region showing. Now if I want to do that, I'll just call my plt.ylim, which is to set the limit, and say, okay, maybe start from -2 all the way to +2. And then once I do that, you see that the limit starts from -2 to +2, and then our plot is confined within it. All right. So you can do same for the x limit and so on and so forth. Okay. So also if you generate your plot and then they do not show up on the Jupyter notebook in the very earlier versions, Python 2 and the rest, after creating your plot, you would have to type plt.show for this to reveal the plot. Okay, so plt.show will then produce a plot out. If I'm going to save the plot into a file too, there's a way to do it. We have plt.savefig. So then I pass in here the file name plus the extension. So maybe I want to save this figure as fig.png. We are good to go. Or fig.pdf. the same, or fig.jpg a small dimension, and that's how it works. But also, if your resolution gets so big, sometimes it makes your image very rough, and so you'd also want to use something that's quite within range. Okay, so that's it. Plt.show will just show the plot out. Plt.savefig will save it to a figure. And like I was saying, if you try plotting in Jupyter Notebook and it doesn't show, then you would have to make use of this percentage matplotlib. Okay, that's the main package. So percentage matplotlib, then leave a space and type inline. That means it should show directly in the line. All right, it should appear on the Jupyter Notebook, and that's it. Okay, so there's some extra information. For instance, we tried producing a sign plot. In this case, the sign of a list starting from 0 all the way to 360, because the range from 0 to 1 less than 361. And then we try to plot this time the values of the angles against the sign. Okay, so we have PLT plot A against B. And then like we said, when we see this curve, we know this curve is not right, because this is just 0 to 360 is just one circle or one cycle. All right, and within that one cycle we expect to have just one waveform if we are producing the sine wave. So then we would have to go back and then apply our degree to radian function on this. So we come back here and then indicate our np.dec2rad on the A, and then we can replot it, and this time we expect that the sine wave or the sine curve looks this way. Okay, starting from, let me set the limit of the y label so we can see it clearly. So we have your plt.ylim to be -1 all the way to 1. Yes, and then we expect that this is how it should look. From sine 0 we have 0, sine 90 should be 1, and then sine 180 comes back to 0, sine 270 will be -1, sine 360 goes back to 0, and that's how the sine wave looks. And the same thing is applicable for the cosine. So let's say we have here C being the cos of the A, and then I decide to plot. Okay, and this is how we expect it to look. That's how the cosine wave will look. At least from our knowledge on the cos and sine wave, we know the blue one is the cos and then the orange one is the sine. But then we can also again set the label like we did. So we have here label equals to sine, and then we also have the label in this case being the cos, and then we can visualize the legend. Okay, I'm using the best location, so that's it. All right, and bear in mind I can also decide which colors I want, so I can pass in here color equals to say red instead of the default color, and then maybe a color here to be say black. Okay, so black is the letter K, blue is the letter B, red is R. I mean, there are a whole lot more colors. You can also type them in full. You can type your red in full, you can type your black in full, and you are good to go. All right, so you then wouldn't bother with what variables to use and all that. Okay, and this works perfectly. Okay, so there are lots more you can do with your PLT for visualization. Okay, so I think that's also explained down here. The same thing has been done this time, adding the labels and the rest. So when you look at this time, I believe you should be able to understand it and be able to reproduce it. And if you have any question, you can always reach us, and we are more than willing to help you. And also you can get access to the various resources we'll put out there to help you. All right, so we are going back to see how best we can apply the two, like merge the things we've done. So the Numpy and then the Matplotlib. So I indicated that if I already have a list, or I have a different data format, say A being a list of 1, 2, 3. In this case, the type of A is a list. So if I want to convert it from a list to array, then I can make use of np.asArray, and that changes this into an array. All right. But then if I'm now recreating the array and I don't have the array from a list, then we can make use of just np.array. Okay, and then pass whatever items we are having in here, and then it will produce the same array for us. So in this case, AR we generate an array of the values 2, 3, 6, and that's it. And bear in mind, arrays are not the same as lists. For Python, the two are different data types. Okay, so they have different behaviors. All right, and then if I want to save this array into a file that's in an ASCII format, I can just make use of np.saveText. All right, open the brackets, and then I pass here the file name as a string. So I'm saving to this file, which is the a underscore values.txt, which is the extension. So I save into this file the data AR. Okay, and like I said, within this parenthesis, if I hit my shift tab, I'll be able to know what it contains. It tells me you would have to save first with your f name, which is the file name, and then your x, which is the data, and then the rest are optional. So I can also format the data. I can pass a delimiter, that's something that will separate one column from the other, and that's it. So there are lots more. So we can also format your data. In this case, by this approach, this one we are saying we want three decimal place format, and then two whole figures sort of thing, and that's it. And same way we can also save this into a CSV format. So just as we did for the txt, we can save this into a CSV, and we know CSV stands for comma delimited files, or comma separated files. So we can pass here what will be the separator for every column. So we pass in here delimiter, and we are indicating that the column should be separated by comma. So it means from the first value of one column to the next value, there will be a comma in there. All right. And again, we can also format the outputs into the file. Okay. So these things are more practical, and so you need to try your hands on it to be able to get more familiar with it. Okay. And then just as we save into a file, we can also read data from a file. So there's a default approach, which is, the read method, or the, open method. All right, and we open the file and indicate whether the file is purely for read, for write, for append. But that's like the very fundamental way, or the very basic way. Not that it's bad, it's good. Yes. Any question, please?
Okay.
So wherever I'm working, it goes there. So let's say I want to be specific on the path, then it means I'll have to specify the path. So maybe whatever path it is, then the file. So it means it will be saved into this file in the path I've listed. Right? But if I don't bring the path, then it means it goes into where I'm working and saves it there. I hope this is good. Um, Adam, is your question answered? So we can make use of the, please come. So we can make use of the load text and then the gen from text. Okay. Um, so there are a bit, some differences in terms of what they are useful for, how you get to apply them. And if you really want to know how it's applied, like I indicated, once I type np.gen from text, I open the parentheses, I indicate my shift tab. The gen from text is actually a bit slower than the load text, all right? But then it also has the ability to cope with missing data. So if I have missing data, I would rather go with the gen from text. But then if my data has no gaps, the load text would work way better. All right. And so over here, we'll be using some data which we acquired from the URL indicated here. And so if you have your notebooks, definitely when you go into the data component, you would see the data set in that data folder. But first, so let's the array we created, which we saved here. So let's rerun this. So I run this as my array, and then I save just the array into a text. Okay. Now, when I save that text, I can reopen that values.txt. So I make use of my numpy.loadText, which is the load text subpackage of the numpy. And then I call the file name and then I indicate the delimiter. Now in this case, I mean the delimiter in that case was just a space, so I just indicate the space as the delimiter, and that's it, and I'm good to go. Right, I'm good to go with that. Okay, so now if I load the text from this file and then I print what the output of the text is, we we get to see what the content of the file is. All right, okay, thank you. Okay, so just as I was saying, so we can use the values we created as a sample. So these are ASCII values which we saved into the a values.text. All right. So we load the data from it using the load text, and then we indicate delimiter being the space, and then we print out the data, and this is how the data is. Okay. We can also make use of the gen from text. So let's say I have here np.gen from text, and then I pass in the file I'm reading from, which is the a underscore values dot text. All right. And oh, okay, yeah. So let me pass in the delimiter. Okay. Okay. Yeah. So actually, that's the file I rather saved. So I think I was just a bit. I was wondering where we had the data from. Okay. So um, yes. Okay. Yeah. So that's it. We only had the data set 236. Yeah. So if we load that file, this is what we are expecting: the 236 from the file a values.text. And when we use the gen from text, we have the same thing showing up. Right. Okay. So we can also again load the data from our CSV format, and then I think I didn't save that one. So okay, so yeah, I rerun this and then that is saved. So now when we open from there, we should be able to. All right, just a minute. Okay, um, I think we created an array called AR, and that's the same one. Okay, let's see. There was a certain array we're using which was multi-dimensional. Just a quick one. Okay, all right, that's all right. So let me try recreating um, the array here. So let's say we have AR being so, and then we produce the AR to see what it contains. All right, that's good. So let me save first. So we have np dot save text. We have a underscore values txt, and we save in here the AR, and we can do the same with the CSV. So np dot save text a underscore values dot csv, and we pass in our AR, and then we can also pass in the delimiter. Yeah, okay. So the delimiter, let's say the delimiter in this case is a comma, right? So that would save it, right? Okay, so now if we load this data set that's from the A values, we expect to have the data we just passed in. And using the gen from text, we can also produce the same thing. And if you are loading the CSV, so we indicate the file that's a values.csv, which is a file name, and then the delimiter being the comma, indicating that the comma separates one column from the other, right? And it gets to read it as such. Okay, and that's it. Um, so there's also this default package. I mean, this path works just like you are working, I mean, trying to locate your subdirectories or trying to move from a directory to the next on your terminal. So we indicate that from pathlib we import the subpackage path, and so path, and then I'll indicate the directory I want to go into, and then that would identify the directory. So if you have the downloaded, I mean, materials we are using, there's a file called data, I mean, there's a directory called data, right? So by assigning this path onto the string data, it means we want to access the data directory and then name that data directory as data path. So if we should run just this path in a separate cell, and then we want to see what the data path would contain, it tells us that we've created a Windows path onto the data directory, right? And once this produces something, means it worked. If it doesn't, if it's a wrong directory, it would produce an error. So let's say I'm opening into data 1. Um, oh, okay, sure. Okay, so not necessarily creating an error here, but then if you are trying to locate it, if you are trying to work from that directory, we'll definitely have an error if you're going to make use of the gen from text. All right, so let's say I have my Windows path identifying the data directory, because that's the name I called that directory, and then I assign that to my data path. So now I'm going to read using the gen from text from that data path, and then there's a file in the directory called nhtemperature.txt, which is a temperature record from the northern hemisphere. That's from the URL I showed up here. So when you go to that URL, you would find that data set. So we just load that data set using the gen from text. So I have np.gen from text, then the path slash the file name, right? Because the path would end without the slash, but then the file is within the file, so I need to bring the slash to make it identify where to get the file. And then I've assigned the output of that data that will be read to the variable temp. Okay, so you can just find the shape, find the size, and all that. So if I run this, it tells me the data contains 166 rows and then 13 columns. So we can equally just visualize the file. So type in temp, and then it tells me there's an array containing all these elements. But there's a whole lot of, huge data set, some chunk that uh, it might not make meaning directly from just seeing it here, unless you know what the data contains. All right. So let's say I want to, so this was to find the very, like we said. Now, if I'm subsetting this data set, which would come to that part, I'm just using it as an example. So the data has two dimensions. So for instance, if I type in here np.ndim, which is the dimension of the temp, it tells us there's a two-dimensional data, which we are thinking of it as rows and columns. All right. So if I'm trying to subset, the comma separates one dimension from the other, and then the dimension here would be the first one. So if I pass here a colon, then it means I want all the elements or all the positions in the first dimension. And then if I also pass another colon, it means I want all the elements in the second dimension. So it means I'll be collecting the whole data, or I'll be pulling out the whole data. But then let's say I want just the first position element on the first dimension. So I can just pass in 0, because the indexing starts from 0. So just as we did for the string subsetting, the array subsetting, and the rest, we can do same. So I just pass in here 0, and this will pick just the first position, so elements on the first position of the first dimension, but all the items on the second dimension. So if you think of it this way, think of it as rows and columns. So this is going to be, I go onto row 1, it means I need just items from row 1. And then you ask yourself, which items on row 1 do I need? I need everything on row 1. So everything along every column on the row 1. But let's say if I just need row 1, but just the first 3 column elements. So I can just pass in here, say 0 to 3. That means I want 0, 1, 2. So this will pick just the first row, or the first dimension, or the first position on the first dimension, and then the first 3 positions on the second dimension. So if I run this, this will give us just the elements on that. So if we go back to our temp and we try to look at just the beginning part, we expect that at least the first part will contain the first dimension, which is the first two. We have 1850. I mean, there's exponent 3, so 1850. There's exponent -1, so we have negative 0.84, and then negative 0.05, and all that. If we come back down here, we notice that the first 3 columns of the first row are the ones that are exactly selected. Alright, so we can use this subsetting approach to pull out data from the Numpy, generated data, or the Numpy read data. Okay, and so that's exactly what the string, the Numpy subset setting or selection does. So let's say I want just the first element within the data set. So I want the first position of the first dimension, the first position of the second dimension. So the intersection of those 2 points is just the first element, which is the first position here where they meet. So the first element, which is the 1850. I want just the first position on the first dimension. All right. And I believe by now when we talk of position, you think of it as index. All right. And dimension is different. So the dimension in this case, this whole thing, the one that's before the whole column, represents a whole dimension. The whole one after the colon, the comma. The whole one after the comma is also another dimension. So we have 2 dimensions. But then we want just the first position, or the first index of the first dimension. And we want the positions, or the index 7 all the way to 9. Because this is always the last -1. So from the 7th, which is in this case going to be the 7th, because you're starting from 0, that will be the 8th index, or the 8th position all the way to the 10th position. But we are doing index 7 all the way to index 9 on the second dimension. So what that would give us is that it goes onto the first dimension, picks just the first position alone, and then while it has picked all the first position elements, it will then look at the first position elements that fall within the 7th to the 9th index on the second dimension, and where they meet, it will just extract that data for you. And that's what we have here. You can also do the same to pick the 10th rows from column 1 to 4, and then we subset the data. So this is all the first 10 rows. So row 1, 2, 3, that order to 10. And then the various columns indicating column 0, column 1, column 2, column 3. That's the first 4 columns. All right. And there are lots more on the subsetting. So maybe I want to pick the data contains dates on the years on the first column. So if I want just the dates or the years, I pick all the rows, all right, but the column 0, okay, and that will bring just the years. Okay, and then we can also again perform basic arithmetic. Now we've done this over and over, so I didn't take my time on this. Using the np, we can do np.min on the data, specifying which dimensions to work on. So for instance, we said the first column contains the year, so we skip the first column, which is the 0, and we start from the 1, which contains the data. So from 1 all the way to the end. And bear in mind the 13 columns you are having, the first one is the year, the next one is data for January, February, on and on till December. So if I want to find just the minimum value for the data set alone without the year, so I indicate, okay, so from the minimum value on the first dimension, we are starting from position 2 to the end. On the second dimension, position 2 to the end. It gives us the minimum value. We do same for the maximum value, and we can echo that out and see what the minimum value is, what the maximum value is. and we are good. We can also do same for the standard deviation along a particular month. So maybe I wanted July data set. Okay, the 0 was for the year, so 1 will be January, on and on, 7 will be July. Okay, so I indicate the column, which is the second dimension, 7, and then all the data sets within the column 7. All right, and so I can find the standard deviation. It gives me the standard deviation value. Okay, all right. We can also apply extra functions on them. So yeah, so I think this becomes more visual. So the data sets we're looking at, this is how it looks. Okay, so we have the year, the January, February, March, on and on to December. So think of it that way. So if I want, let's say now this, we are using this data set. Okay, now skip the full data we are having starts from like 1850. So let's say that's not what our emphasis is on. Let's look at just this part. If I want just the first item, which is the 2010, I come to the dimension 1 is the ones that are going horizontal. Dimension 2 is the data pulling itself vertically. Okay, so if I go on the first dimension, I pick the position 0, which is all these ones, and then maybe I want the first element of the second dimension. So now the first element of the second dimension, that's the ones coming down, would also be this one. Now where they intersect is just this point, so then I pick just the first value. So if I want, say, the first 3 elements of the second dimension along the first dimension, first element, so I pick the first element on the first dimension, the first 3 on the second dimension. Where they meet, that's the data that's pulled out. All right, okay, so our data set is quite huge. So if we extract within the rows, let me use rows and columns to represent them. So the row dimension, we extract 160 to 167. That's data for the year 2010 to 2015. And then if I extract just the 0th index, which is the first position, it would produce just, so after picking all the rows, it picks the first column, which is just the year, and that's what we are having down here. Okay, right. And so we can just extract the data from the column, the index 1 to 13, which is the second column to the last column, and that's just the data for the various months, and apply the mean on that to get the monthly average data. And then bear in mind we are applying an axis of 0. Like I said, there's a two-dimensional data, so we have the first dimension, the second dimension, but bear in mind Python indexing starts from 0, so Python treats them as index 0 being for the rows, index 1 being for the columns, or index 0 being for the first dimension, index 1 being for the second dimension. So if I want to collapse the first dimension, I want to collapse the rows, so I'm averaging over the rows, then it means I have to find the axis over that dimension that gets collapsed, and then we would only have the column, the column form averages. If I want to do same for the column by collapsing the column, then I would apply the axis of 1, and this will produce sort of the row averages, so the average along every row because the column is collapsed, right? And that's how it works. So we can do that, try that on various data sets. Okay, all right, now we can also combine the Matplotlib together with the Numpy. um, so we would want to visualize the data, so we are going to use the same data, we are not going to change the data, so we can get a clear application of what to do. Now in the first instance, we're just looking at how to create a single plot. But if you want to create a multi-plot, say you want a plot that has multiple panels, then what we can do is we create first the figure environment. Okay, you notice the first time we didn't create the figure environment, we just plotted because by default once we plot it would assume one main interface to work with. So we can first create the figure environment by typing plt.figure, and then that's a function, so we open and close, and then this will create a figure environment. All right, and if you want to add subplots, so we would want to first assign this to fig. That's like the one way of doing it. We'll first want to assign this to fig, and then we can then add the other items we want onto the figure interface we've created. So we would want to, for instance, create an axis. We want every panel to be a separate axis. So let's say we have AX, and then we are adding that subplot onto the fig. So we have fig dot, and then I can tab to know what comes within the fig. So a whole lot of things coming. So we want to add subplot. Okay, and then by adding the subplots, let me run this first and then we go back. So if I shift tab in this, it tells you what to indicate in the subplots. Okay, so a very basic way of identifying the subplot is that we have, let me go back and use this, maybe this would represent it. Now don't think of this as data, think of this as a whole figure frame or figure interface, and I want to give every individual box to represent a particular position of a figure frame. Now when it comes to the figures, we don't start from 0, it always starts from 1 because the figures are treated as whole values. So I would need to specify the number of rows of the figure I want to create, the number of columns I want to create, and then I'll specify exactly which position I would want to place the figure on. So let's say I want to create a panel plot that has about 2 by 2. Okay, so then I'll specify first the number of rows, which is the 2, the number of columns, which is the 2 again, and then because the position in this case starts from 1, maybe I want to place my figure in the first position, then I would indicate 1. That means it should create a 2 by 2 subplot environment. And then for the first plot I'm going to generate, or whatever is going to come after this, it should be positioned in the first subplot. So let's say I want to create just a plot of 10 random numbers. So let's say plt.plot, and then we are plotting np.a range of 10. Okay, now if I plot this, this has been positioned in the very first location. Now let's say I want to plot another one in the position 4 so that it becomes clearer. So let's say I create a new axis. I can create maybe the same ax to overwrite it, or let's say ax1, and then I add subplots, fig.add subplot, and I indicate the row. Again, the number of rows are 2, the number of columns are 2, but then position 4, right? And I'm saying plt.plot, and this time I'm going to plot the same a range of 10, but I want to multiply each value by say 5, and then you can see it. So now this goes into the first position. So we have like 1, 2, 3, 4, a 2 by 2. This goes into the first position. The second position is here, the third position is down here, the fourth position is down here. So you can use this to specify exactly where you want your plot to be, and then you add onto it. All right, and so that's what this has explained here. So we have a fig.add subplot. We specify, okay, there's a 1 by 2, that's 1 row, 2 columns, and go to position 1 and just set a title. So it does that. And then the second one, 1 row, 2 columns, which is the same interface we created, but go to position 2 and set a title, and then it does that, and we are good, right? So there's one approach. Now the question you ask is, what if we are creating a multiple panel of about 5 by 5 and I want it to be in position say 15? Can I just write say np dot add, fig dot add subplot, and then just pass here say 5, 5, 15? It would always need just 3 values. Okay, it doesn't need more than 3, because when you do this you get the system confused. Is the system creating 55 rows by 1 column and then going to position 5, or creating 5 rows by 51 columns and going to position 5, or creating 5 rows by 5 columns and going to position 15? So you have to be explicit. So this is where commas come in handy. So you can separate them with commas, say 5, 5, 15. That means 5 rows, 5 columns, position 15, and then it would know exactly where to place that plot. All right, and you can do same even with a 2 by 2. We could have done same, so 2, 2, 1. Okay, and then we do the same, and it will still work perfectly for us. Okay, and so that's how you go around it. Now this is one approach of creating plots. There's a second approach, which we will just use the plt.subplots. Okay, so the second approach is that now I know I'm going to generate subplots. So all I would need to do is, I don't need to create the figure environment by using the plt.figure and then now adding subplots onto that figure and calling them axis. I can just call here my fig and then my axis, say AX, or we can use axis, all right? And then we pass in here Plt.Subplots. Now this time it's plural, so from the Plt there's a subplots subpackage. So we have Plt.Subplots, and then we can specify the figure size. Okay, that's okay. The figure size should be this by that. So if you don't specify, we'll just use inches. So that's like 5 by 5, 5 by 5 inches. All right. Now we can also specify the number of rows and the number of columns in this. But this time we wouldn't specify the position because this is just creating the environment. It just creates the environment for us. So if I run this and then I type my axis, okay, because I haven't specified anything, the axis is just one axis. So if I print axis, it tells you it has created an axis subplot interface. Okay. Now if I want to generate multiple, I can pass in here n calls, which is the number of columns. So maybe I want 3 columns, and the rows, maybe n rows, to be also 3 rows. Okay. Now if I print the axis will have about all these 9. Okay. Let me print that here. So you look in here and it tells you it has 1, 2, 3, 4, 5, 6, 7, 8, 9. It's created 9 different positions. Alright. And because I made it a 3 by 3, it's kept it as such. So I can pick any of the positions and tell the plot to go specifically to this place. So let's say within this axis I've created, I want it to go to position 0. Now this time I'm going to use the 2-dimensional approach because I created a 2-dimensional visualization interface. So then I would subset this axis and say, okay, go into position 0 on the row, 0 on the column. Okay. Now in this case, we are going to use the Python indexing when we are using the axis method, because this one is working as an axis subsetting, sort of working the same way as the Numpy subsetting, which is different from when we are adding subplots. Alright. When you just do fig.add subplots, then it means you are going to deal with whole numbers and you can't start from 0. But then if you are using the axis approach or the axis approach, it means this axis is created as an array, which you can see from here. So if the axis is created as an array, then we are going to treat it as an array. So we can do an array subsetting and say, okay, go to the array position 0, 0, which is 0 on the first dimension, 0 on the second dimension, and create something. Let's say we just want to add a title. So let's say title hello. Sorry, I'm supposed to add, yeah. I think it's set title, yeah. Is it set or add? Yeah, set title. So you see now it produces all the 9 and then goes into the first position and just says, okay, hello. Now I can just randomly pick any of them. So let's say I want to go into the 5th position, which is 2 on the row, 2 on the column. So I can change this to 2, 2, and then the hello would go directly there. Okay. Oh yes, I made a mistake. I also forgot that I just something I just explained. So Python indexing starts from 0. So by 2, 2, I'm not looking at this one. 2, 2 means 0, 1, 2. So 2 would be in the bottom 2. That's why I came over here. So if I want that, that should be actually 1, 1, not 2, 2. So 1 on the row, 1 on the column, and then I have it as such. So we have the hello printed on top of it. Right. So that's another way of creating the subplots. Now, let's say I'm having this plot and it's, quite all over the space. I mean, I want to create spaces in them. I can do a subplot adjustment. So from the PLT, there's what we call the subplots adjust. So subplots underscore adjust. Alright. And then I can specify the margins of my figure interface. I can also specify the spaces. So I can specify, bear in mind the left hand side, think of it as you using an A4 sheet. The absolute left is a value of 0, absolute right is a value of 1, the bottom is a value of 0, the top part is a value of 1. So you can actually adjust in ratios between 0 and 1. So if I want to move this from the left, it wouldn't show directly here because I'm not outputting. When I print it out into a file, that's when you'll be able to see it. Then I can specify exactly, okay, so start the left hand side from say 0.2. So it wouldn't start from the far 0, it would give some margin. And I can also specify the right because the right starts from 1, I can then reduce it. So maybe let the right be at 0. 0.8. So it means about um, 20% on the left hand side, 20% on the right hand side, margin will be left. I can do same for the top and bottom. All right, and that works. And then also, if I want to create the spaces, the way the figure is, I mean, it's all together. The hello is not directly showing on the subplots we want it to show. We are confused whether it is a Y label, I mean, an X label for the first one above, or it is a title for this one. So then we can adjust using the spaces. We have the H space for the height space adjustment. We also have the W space for the width space. So if I adjust the height space, say by a value of 0.5, then I expect that it would create the spaces between the heights. Okay. Let me increase the fixed size to say about 8 by 8, so it's clearer. All right. And so we have this. We can also adjust the width space by using the W space approach. So maybe 0.5, and then that also spaces it out clearly. All right. And then, like I said, since we are making the axis, we've made it. I mean, we've made our axis an array. We can just call any of the positions and then just perform whatever visualization you want to perform on that particular position. All right. So comparatively, I think this is way easier to go by, but it also has its own, shortfalls, especially when you want to merge a spatial plot with a sort of a time series. Let's say you have a map visualization on one. It means you would have to pass in here a keyword, which maybe we might look at in the latter parts. And when you pass in the keyword, it means that keyword affects all the axes. All right, and so treating it becomes a bit technical, and you need some expertise to do that. But I mean, it's nothing that cannot be done. It's something very simple. All right, so we see in here the example just similar to what we did at first. Now, in this case, default row, default column, so it means there's a one panel plot. All right, and it creates the X label, the subplot, and the rest. And in this case, we have two columns created, but the rows were not specified, so it means just one row, two columns, and we use the axis method. So if it's two columns and then just one row, bear in mind if I run this and I print just the axis, okay, you would notice that the axis is an array of just, I mean, 2 points. All right, so now if I find the length of axis, it's just a value of 2. If I find the shape of axis, sorry, np.shape in this case, but I could have just done axis.shape. Now this produces just a one dimension, okay, and since it's one dimension, that's why even though we have two columns and it's purely one dimension, if it had been just rows and there's no column, it's the same thing. We can't use the comma approach. All right, we just have to use the, I mean, individual position, because it treats it as a vector. I mean, this is just like a vector, not necessarily like a matrix sort of thing. All right, and if you remember from the very first lesson, I indicated something that sometimes this is where the you know the modulus and then the floor division comes in handy. So now let's say we just want to create this plot, okay, and we are going to only add titles to it. So let's say we have a list of titles here, or we call them just labels, and we are just going to pass in names. So let's say the names are, yes, any question please.
Yeah, please, when you type this one, the shape of the array, it
Mm,
gave you two comma.
yes.
But I don't know. We have two charts on a row. So
Mm,
I was thinking maybe the outputs might be maybe 1 comma 2, because you have one row and two columns. So I don't know the two comma. I don't know how you are going to, or maybe the user is going to get to know that it is representing two rows and
okay.
maybe two columns and one row.
All right, so is this, by this array we created, we only specified one dimension, which was the columns, okay? So it, by intuition, when you think of them as rows, columns, that's where maybe a bit, it might be a bit skeptical to get the right import. But when you think of them as dimensions, we only specified the number of elements on a particular dimension. So if you look at this, when we type the shape, it tells us, okay, we have just what's it, two elements. The shape is supposed to give us the respective sizes on every individual, dimension. So let's try to look at this. Say we have A being 1, 2, 3. All right. Now this is just a one-dimensional data. That means it has just, maybe think of this as just rows, right? I mean, it has just one row and say maybe three columns and all that. Think of it that way. But this is just purely one-dimensional data. If I find the shape of this, I expect it to give me just the number of elements, that's the size within that particular dimension. Now, think of this other one. In this case, I'm separating them up. So we have, say, 3, 4, 5, and then we close it up. Now, this is a multi-dimensional data, right? The comma is separating definitely one element along a particular dimension from the other, all right? And then each individual element also is representing elements along a particular dimension. Now in this case, if I run this, I expect to have the sizes on the two respective dimensions, which means on the first dimension, which is the horizontal lines, we have two elements, okay, or two, let's say a length of 2. The first one is 1, the second one is 2, all right? That gives us the 2. And then along the other dimension, which is the vertical ends, we have 1, 2, 3. So it gives us the number of items on the second dimension, right? Now we can only tell from here that there's a two-dimensional data because it has a first dimension, comma, a second dimension, right? And it's telling us only the sizes along each, or the length along each dimension. Now when we did same for the axis, and we typed in the np.shape of our axis, this told us that we only specified elements along one dimension, all right? And that is purely different from when I've specified the rows and columns. When I am specific on the rows and columns, then it means I have a set number of rows, set number of columns. But in this case, I specify just one dimension, so it gives us just the size or the number of elements along just that dimension alone. And that's why you can't have the 1, 2 in this approach. Okay. So,
Okay.
yeah.
Thank you.
So yes, I was going to explain something over here. So let's say we create just random titles. I think I started creating it somewhere up here. Okay, let's just go ahead. So let's create some labels, just generic labels, and call them, say, hello, OneQuantum. Sorry. We have, say, Ghana. We have, say, let me use Adam. Let me use your name, okay? So we have Adam, and then maybe let me also use Docus, and say maybe PY4CA. Yeah. So let's say we have these 6 elements within the label. So okay, we have 6 elements within the label. Now let's say we are trying to create the same fig and axis. Okay, so we have fig, comma, axis, or axis in the plural form as Plt.Subplots. All right, and we specify the columns. Let's say the columns are 2, and then our rows are 3. Okay, and we have a fixed size which we can specify, maybe anything. Say, let's use the same 8 by 8 in this case. All right. And then after I've created this, when we look at the axis, we notice it gives us okay, yeah, I did a typo, and it should even be fixed size equals to, yeah, so the fixed size should be equated. All right, so when we look at this, we have 2 columns and then 3 rows. All right, now I want to place the header throughout all of them. I don't want to start, okay, axis 0, 0 dot title, maybe dot set title, then I go into picking the labels, and then I pick label 0. All right, this would work. I mean, this is perfect, it would work. But what of using something with length? Okay, We saw yesterday that we can create an enumerate over the labels, and that will give us the position. So for instance, if I have enumerate on the labels, that would give us both the label, I mean the positions, the label positions as well as the labels. So if I have this, and then for instance I pass in here a for loop, say for um, the index, and then the libs, all right, in this enumerate function. Now let's just print this out to see what the output would be. Okay, so we are printing out the index and then the labels. All right, let me comment these ones for now. So if I run that, we know that all the labels have positions. Now think of it this way: if I find the index, okay, let's say 0, if I find 0 floor division 2, that gives me 0. If I find 0 modulus 2, that will still give me 0. If I do same for 1, that will give me 1. If I do same for 0, 1 floor division 2, that will give me 0 because 2 cannot go into 1. So the integer form of 1 divided by 2 will be 0. Now, if I move to the third one, this will produce 1 because the integer division after finding 3 over 2 would be that. And then if we find the modulus, we expect to have also 1. So you notice that if I'm doing this and then I've set, because I know my columns are just 2, so I set this value as my column, which is a fixed column, I mean the fixed length of column. I can just be dividing the index and be getting zeros and ones, or I mean getting not necessarily zeros and ones. I'll get zeros and ones as the modulus in all the case, but then I'll get the integer value for the division. All right, so let's say if I get to position 5 and then I find the modulus, that will give me 1, all right, as a remainder. But if I do the floor division, it will give me the integer form. Okay, so think of it this way: since I'm getting the maximum in this case can be 2, and then the maximum modulus can be 1, and then I go back to this axis we created, we can see that the axis in this case we are talking of 2 columns, 3 rows. So it means we can go to a maximum of 2 comma 1 to be the position. So let's go back and then replot this. Let's just show our axis again. Now you notice the axis. If you are using the position, this is 0 0, okay, based on the axis as an array: 0 0 0 1, 1 0 1 1, 2 0 2 1. So we can use a combination of the floor division and then the modulus just to identify this without necessarily coming up here to specify all of them one after the other. What if we are not just what if we are doing something repeated for all the plots, okay, and there are a whole number of lines that we are going to repeat? Then we can just simply do that combination and we skip it and we are done. So let's say in here I can decide to call my AX, right, and then I go back to the axis, and then I'm saying that, knowing clearly well from what we did, we noticed that the row would be changing. So if I change my row based on the floor division, that okay, the row should be the floor division of the index by the columns, okay, which is in this case say 2. So when it's looping through, whatever the index value is, it would do a floor division of that by 2, and that will be the position on the first dimension. And then I want to do same with the modulus for the position on the second dimension. And of course we know from here that the second dimension, which is the vertical part, can only be 0 or 1. So the modulus would be producing just 0 or 1 in this case. So if I do this, it is very simple from this part just to then have my AX, because I've already assigned whatever floor division and the modulus division marking the positions of the axis. I've assigned them to AX. So I can just call AX dot maybe set title, and then I'm going to set title on the labs, because at every particular index the labs will contain the label we are looking at. So I pass in here the labs, and then as simple as that, it names all of them, it gives them all the title. So I don't need to go through one after the other and be spending time to do all things. So let's say I have different data sets. All right, let's pick the same. I believe we still have our data there. AR. Okay, no, not this one. The one we're using from. Let me just check up here. Okay, yeah. So we can use our temp. Okay, so let's call this. Um, okay, so I want to pick just these parts. Um, so all right. So let's say we have data now being okay. So all the this particular row, we don't want the year, so let's start from the one. Okay. So now if we go up here and then we type in the data, we should see what the data contains. Okay. So the data contains about 12 different columns of, data sets. Okay. And then in here, I just want to plot and see what happens. So I decide to pick, for instance, let me also name this one the years. Let me call the years from this same thing. I just want the column 0 alone, which will represent the years. So of course, if you type in the years, you notice that the column 0 is just the years that we want. That's it. So I want to plot um, the years against the particular data. Okay. Uh, or let's go in for a longer period. I think this is too short. So let's go in for something long enough. So let's say maybe from 120 in both cases. All right. Now, so we have the years, we have the data. Now, when I get here, I'm going to plot within the particular axis. So I don't need to go back to Plt.plot because I'm going to use the axis to plot, right? I can still make use of the Plt.plot, but it means when I make use of Plt.plot, I need to specify here, after plotting the thing I want to plot, I need to specify what the axis is going to be. Okay, so there's this keyword AX, which you can use that to specify that, okay, the AX, which is the variable, should be assigned to this axis we've set here. Okay, that's it. So we can go by this approach, or we can simply go by, okay, I've created this axis already, so let me just pick this axis and then plot the years, of course, because the years is just one dimensional data, which is just one column, and then plot it against, say, the data. All right, I want all the rows, but I want a particular column, so the column should be based on the index, for instance. Okay, and let's say this is January, February, we have here March, we have here April. There are multiple ways of doing this one, so but we are just trying to make sure we understand. Okay, so we have this. Now I'm saying that the plot should be based on all the rows and then the particular index we want, which is going to be the column. All right, because the index will be based on the positions derived from the labels. So if I now produce this, um, okay, yeah, so it worked, but then I think the only thing we are skipping here is because we've specified the columns to be just 2 and the rows to be 3. Okay, so let's make this maybe a 3 by 4 so that we have all the 12 of them. So 3 here and then 4, and then let me change this to be the number of columns, which is a 3 3 instead. Okay, and we replot. Now this produces all the data sets for the various months. Okay, it produces all the data sets for the various months. Okay, so with this you can just in one line produce your output and you are good. All right, maybe let's pass in the adjustment so that Um, so I'm just going to duplicate this there so that it's spaced out right. Okay, and then that's it, and we are good to go, right? So I don't need to pick all the data sets one after the other and try to see what's in there. I need to just, I can run it through like that, and then I get my output, and then it goes into all the various panels. And that's how powerful the floor division and then the modulus um, combination works. Right. Okay. So there's an example from here, which is just the time series plots. I mean, since I've already run you through the basics, I wouldn't go through this again because, I mean, I'm sure we should be able to understand how this works now. And then in this case, we try to generate just the plot, and these are just our anomaly data. So, and in this case, we use just a single subplot because we didn't specify the rows and columns, all right? And so when we just call AX, it's referring to that axis, so we can overplot on that same axis and then do a whole lot of things to that. So, I mean, once you have your data, it's very easy to visualize it, okay? And I mean, that's some extra on it. Um, I think we are a bit stuck with time, so maybe I'm going to skip some of these ones. Um, but there's some extra information there to explain what we are doing. So we can also produce bar plots, histograms using the Numpy, the Matplotlib. You can also generate, I mean, pie charts as well. And then the only thing to note in here is that the explode we are having here is just talking about, I mean, how spaced out the pie should be. So for instance, this one has a certain value. I think this is for November. So if I look through, November should be the last but 1 month. So that's like 0.2. So it gets space from the center about 0.2. If I should increase this to say 0.8, it gets open the more, right? So you can also take note of that, and that's it. And yeah, that's just by way of the pie chart. You can also produce scatter plots. I mean, for time's sake, I would wish that you try your hands on this and then communicate back to us what your experience were. We can also do some um, visual, I mean, sort of 2D plots with some labels on them. These are just what we call the heat maps. I mean, those who have been watching football nowadays, you notice, I mean, whilst the game is going on, especially EP or whilst it's going on, they tell you the runs the person, one particular person has done, and then which places he's been to the most. I mean, all those heat maps, you can also generate something similar using this, a combination of IoT and that. Right. And then we can, I don't know if I still have the time to go on, but I think we can, maybe you can spare me some 10 minutes so that I try to run through this a bit, but I hope we understand it. So for spatial plots, we can make use of the Cartopy feature or the Cartopy package to produce spatial plots. Now, simply if I want to make use of Cartopy, I just import Cartopy and I'm done. And under Cartopy, there's what we call the CRS, which deals with the resolution. I can also import Cartopy and then just say, okay, from rather than importing the Cartopy, maybe I want to import just the CRS. So from Cartopy, import CRS, and then I just give it a name, say maybe as CCRS, which is like a default. Everybody understands this. That's like the Cartopy CRS or CCRS. Now, if I've installed this already and I run this, I don't expect an error. Okay, so once I import my Cartopy, I have the CCRS, but then there's also what we call the feature. So I can also say from Cartopy import the feature. Maybe I say CF. Now the feature here contains the various features like the boundaries, the rivers, the lakes, and the rest. Okay, so I'm going to create just a simple plot. So let's say we have plt dot figure. Okay, and then, or maybe let me just use this one to explain. That'll be straightforward. Um, so we have this. I mean, I think I indicated two ways of doing it. So in this case, we have the plt.figure, we specify the fixed size, and then we assign that to the figure environment. And then we create the axis. And in creating the axis, we specify what kind of projection, right? In CRS, once we've imported our CCRS, when we type in CCRS dot, we'll see all the projections and extra information it contains. So you can create maps on any of these projections. So the first approach is we can use the AX assigned to plt.axis and then specify here the projection type, okay, that we want to create this projection. This is one approach. There's also, in fact, there are actually about 3 approaches. So let's say we have this, I create my figure, then I come to plt dot say subplots, all right, and I specify maybe 1 1 1. Then I can pass in here a comma and specify the projection, and this should create the projection for me. So what's the error here? Figure object has no projection. Okay, let's see. Okay. This is one of the ways that I rarely use, so I'm just trying to remember how it works. Yeah, okay, so that's it. Yeah, so we can set the figure to, I mean, we create a figure and set it to fig. We add a subplot, and remember the subplotting we did. So 1 1 1, this means 1 row 1 column position 1, that's it. And then we'll pass in the projection and indicates the projection type we want, all right. And once we are done with this, it means we can work with that whole projection and we are good to go. This one approach. Now the second approach is that we created a figure, and then we, in creating the axis, we said that plt.axis should be dependent on this projection. That's the second approach. Now the third approach is where we're using the axis method when we're creating multiple axes, and we said we can just have plt.subplot, specify the number of columns, the number of rows, the fixed size, and the rest. But in that case, if I want to specify that this should be a map projection, then we have to specify this subplot underscore kw, that's the quarks. So some auxiliary arguments. So we indicate subplot underscore kw, and then we'll create a dictionary of the arguments that should be added. And one of the arguments we are adding within the dictionary is the subplot. I mean, sorry, the projection. And then we'll specify what projection to use. That's ccrs.plate carry. All right. So once we do that, let's say I have. Let me go back to the first one I was using. So let me assign this to axis, which is ax. Okay. So once I have this, I can just generate my coastline. Say this axis, that's ax dot coastlines, and then I open and close the method, and that generates a map of the entire globe for me. All right, maybe you want to be specific. I want to just zoom in over a particular continent, say Africa. Now I need to set the extent, so I have ax dot set underscore extent. Then I pass in here into square brackets the various positions. I hope I remember the dimensions, how it goes. It should be either anti-clockwise also. Yeah, so let's say this is going to be the left. So let's use about say negative 25. The bottom, let's say about say negative 40. That's the longitudes and latitudes. The right, let's use about 45. That's towards beyond Kenya. And then the northern part, let's use about say 35 and see if it works. Okay, so we had something else. So I think it should be rather this way. So negative 25, 25, negative 40. Yeah, so this is the right approach. So it should be the left, right, bottom, top, not in the clockwise or anti-clockwise. It's rather the left and the right, and then the bottom and the top. Okay. So once we have this, we can zoom into the particular area, and then we visualize whatever we want to visualize over that area. Oh, sorry, how am I doing? Okay, so this rather should change. Okay. All right. All right. So maybe I want to add a scatter plot. So I can just add my ax.scatter, and then maybe specify some particular point. So maybe let's say negative 2, and then say maybe 7, and then just add a marker at that point of a size of me about 300, and then the color should be, say, red. Let's try it and see. Yeah, so this gets positioned somewhere within Ghana. All right, now once we have this, so we can overlay our plot, our map, and then superimpose a plot over it. Okay, that's possible. Now let me comment the scatter first so that we still have our map. Now once we have our map, maybe you want to indicate the regions in there, the various countries. It means I'm going to add a figure. I'm adding a feature to the axis. So now in this case I have ax dot add underscore feature. All right, then I'm going to add the feature. So now the feature I'm going to add, for instance, is the country border. All right, that should come from the CF we imported. That's the Catopy features, because it contains a host of features. So I pass in here my CF dot say borders in uppercase, and this should give us all the country separations. So based on this, we know clearly that what we plotted was identified somewhere in Ghana. Okay, so yes, and there's a lot more. So there are a whole lot of features you can use, you can actually look at, and there are lots more things you can do. So as we go through this, you'll be able to get familiar with it based on the explanation. So we set the extent, and then also if I'm not going to use the default projection, the default country boundaries and the rest, maybe I want to make use of my shapefile. You have downloaded your shapefile in the .shp format and want to use it. Catopy has a feature to do that. So in that case, you are going to call the add geometries. All right. So you adding that to the axis you created. So the ax dot add geometries, and then you are going to add the shapes. But bear in mind the shapes you are having here should be red from this. Okay, so we have the path specified, and then we go into our list, and there's a package called shape reader which we would need to import from the Catopy subpackage. So catopy.io.shapereader, we import shape reader, and we use that to read the shapefile. So there's the shape reader.reader, and then we read the shapefile. All right. I don't know why we put the string here, but the string actually already is in the string format, so it still wouldn't have any feature, any impact on it. So we read that shape path to where the shapefile is, and then we pick just the geometries. Whenever you read the shapefile, it has lots of information, but emphasis here is on the geometries, so we indicate the dot geometries to pick out just the geometries, and we create a list of that based on the list method, and we assign that to the variable administrative shapes, that's adm1 shapes. And so from here, when we come back here, now we can add that adm1 shapes that we created to our axis by using the add geometries, and then when we run that, that should produce I think I need to go back and run this. So import all my packages, take the path, and then I think I can skip all these ones, reading the data. Now read the shape files, and then I can come down here and then run this, and this should work. Right. Okay, so it's taking some time. I think this is the first time I'm running it today, so it will just take a little bit of time, but it would show up. Yeah. Okay, and so while we wait for it to pop up, I think that should be it by way of what we have today. Yes, and then exactly, and then so we have a visualization over here. Okay, and these are just sort of rainfall data from various locations. All right, and that's it. And we have some trial questions for you to try your hands on. And as a way of recap, I don't know if we have some questions before I get there. Wow. So Adam and the others, I think when you take the time, because the materials are very detailed, when you take time to go through, it should be quite easy for you to understand. And if you have any question, you can always reach me. When you go back to the notebook 1, it contains the various contact information. So yes. So when you go through that and you have any challenge, you can reach us on the very first lecture, the we had the contacts indicated in. And then also, like I said, when you're going through the materials, there are various comments in there to help you. So, I mean, with the comments, you'll be fine. And there's nothing much. I mean, just something simple for you to get familiar with. And once you get it, I advise you try your hands on this particular task. Right? I mean, the truth is over here. I mean, there's no way to really see whether you are doing it or not, but the real dignity lies on you to make sure you get your hands at least working on this trial test. I mean, this is not to make you a pro level, I mean, programmer or analyst, but then this only to sharpen the skill and make sure at least you have a fair understanding of what you are doing. And then when we come and you have any question, you can always reach out to us and we'll be more than willing to assist you. All right. So as a quick recap, we've tackled, I mean, loading packages and making use of the packages. We also zoomed into Numpy, SciPy, Matplotlib, and even did more. Looked at CattoPy and the rest. So we also looked at how to read data from a file, subsetting, applying functions, and then visualizations. And then we ended up with some spatial plots and some examples. And, and so that's by way of what we have for day 3. Yeah, so yes, that's by way of day 3. I don't know if there are any questions. I could take them now. And our time is already it has been exceeded by 13 minutes, but maybe we'll have some 2 or 3 minutes for some questions if there are any. And also for the lecture materials 4 and 5, I believe 4 would be up today, and then 5 might be up probably by morning tomorrow. Yeah, so you can always check back from the GitHub page and then find the materials for your use. Okay, so any question? So please, it's time for questions. So if there are any questions, we probably would take them now and then address them. Any questions, please? It might even be something you already know, but you're still asking for at least the benefit of everyone else. I mean, that's still welcome. All right. So if there are no, okay, I think there's one down here. Let me see. All right. Sorry, guys, but I mean, this is one of the downsides of online sort of teaching. We try as much as possible to make sure you understand it, but you can't really have a fair view of how everyone is progressing. That's why we hope that you would ask questions and then we can be able to assist you. And then, I mean, but if there's still any challenge, the materials are still online. They are still on the YouTube page, on the GitHub repository. You can always get them, try your hands on it. If you have any issue, get back to us, Vami. We would love to really hear from you and know how well you're progressing with the Python journey. All right, so if there's no question, I guess I'm done. Dorcas, over to you. Thank you.
Yeah, hello.
Yes, please. So we are done. Over to you.
Oh, okay, all right. Thank you so much, Dr. Aye. We are grateful for another wonderful session today. And we want to say thank you to our participants as well. And we are still encouraging you to make use of the notebooks, try the exercises, and even try more as well. You can contact Dr. Jeffrey. If you look at the first work notebook of on GitHub, you realize that his details are there, so you can contact him with your questions and other exercises you try as well. And tomorrow we'll meet again at 9:30. So 9:30 you can be on gather to ask questions since our mentors will be around to assist you. Then the main workshop starts at 10 o'clock a.m. Kindly invite your colleagues to join as well. There was YouTube live stream, so you can still go on YouTube if you missed any part to rewatch the lesson again. Thank you so much. So we meet again tomorrow for day 4. We are saying take care
And then just a
and
quick
work
one. I
hard.
think I think
Thank you
we
all.
might also have to take probably a group photo maybe one of the days. So maybe Thursday, maybe that's maybe tomorrow or Friday we might communicate so that at least we can have memories of everyone who was here present. So maybe you can put on your hallelujah dresses. Okay, so see you all tomorrow. Bye bye.